In this video, we will prove the theorem that similar matrices have identical characteristic polynomials, and if they have identical characteristic polynomial, then they also have same eigenvalues or trace or determinant. Why? Because if they have same characteristic polynomial, then from characteristic polynomial we can get the eigenvalue. So if they have same characteristic polynomial, that means they have same eigenvalues. And what is trace? Trace is sum of eigenvalues. So if they have same eigenvalues, two matrices, then sum of the eigenvalues is the same, so their trace is same. Also, what is determinant? Determinant is product of the eigenvalues. So we will prove this one. Now proof. Suppose the two matrices, suppose A and B, A and, or we can write the two matrices A, B is a square matrix. Okay. So n by n square matrices are similar. So by the definition of similar matrices, we know that is there exist a non-singular matrix P also square matrix, okay, such that, so by the definition of similar matrices, if A and B are similar, then there is a non-singular matrix P such that B equals to, B can be written as P inverse AP. What is non-singular means? Non-singular means its determinant is not 0. That means there is no 0 eigenvalues. So if A and B are similar, then we can write B equals to P inverse AP. Now for the matrix B, what is characteristic polynomial? Now the characteristic polynomial of B is determinant, this is determinant sign, determinant of lambda I minus B, where this lambda are the eigenvalues of the matrix B. So this is the characteristic polynomial of the matrix B. Now what we can write? Now determinant of lambda I minus B can be written as determinant of lambda, instead of I we are writing P inverse P minus B. So P inverse P is the identity matrix I. Now since lambda is constant, so we can change its position. So we can write P inverse lambda P, and what is B? B is P inverse AP. So B is P inverse AP, and this can be written as, so determinant of P inverse lambda I minus this A times P. Okay. Since we take out P inverse, so there will be I here, identity matrix here. Now we know that determinant of, if there is two matrix A, B, then its determinant is determinant of A times determinant of B. For true matrix AB, is determinant of A times determinant of B. So from here we can write, so determinant of lambda I minus B can be written as here. So if we distribute the determinant sign, so it would be determinant of P inverse times determinant of lambda I minus A times determinant of P. Okay. Now we know that determinant of any matrix A inverse is 1 over determinant of A. So determinant of A inverse equals to determinant of 1 over determinant of A. So here we can write 1 over determinant of P for this one times determinant of lambda I minus A times determinant of P. And determinant is just a number. So this is a number, this is also a number. Okay, so we can cancel it out. So if we cancel this two number, then we have only determinant of lambda I minus A. So the characteristic polynomial of B and the characteristic polynomial A are same. Okay, so this is the which is the characteristic polynomial of A. So this is the characteristic polynomial of A. So here we use two properties, that determinant of AB is equals to determinant of A times determinant of B, and determinant of A inverse equals to 1 over determinant of A. We use these two properties here. Now, as I said before, if their characteristic polynomial same, and we know that if we set lambda I minus A equals to 0, this is the characteristic equation, then we will get the eigenvalue, right? We will get the eigenvalue. And if we set characteristic polynomial of B equals to 0, then we will get lambda, right? So since this one and that one are same, so lambda would be same for A and B. So the eigenvalues would be same for both A and B. That means their eigenvalue is same. Now what is trace? Trace is sum of eigenvalue. For a matrix, trace, okay. Suppose if lambda is 1 and 2, so here would be same 1 and 2. So what would be trace here? So trace would be trace of A trace of B. Trace normally written TR. So trace of A equals to trace of B would be, so let's do it 2 and this is 3. Okay, so the same 2 3. So what would be trace? That means 2 plus 3, which is 5. So trace is same for both matrices, and the determinant also same. What is determinant? Determinant is defined as product of eigenvalues. So what would be determinant of A? So determinant of A equals to determinant of B. So we need to multiply these two eigenvalues. So 2 times 3, which is 6. So their determinant also same. Now the last part, we need to give an example to show that the converse is not true. That means even the two matrices have same characteristic polynomial, but they are not similar. We need to give an example for this one. So example, let A is a 2 by 2 matrix, 1 0 0 1, and B is another 2 by 2 matrix, 1 1 0 1. Then what is their characteristic polynomial? Then characteristic polynomial of lambda I minus A lambda I minus B is, so 1 minus lambda, 1 minus lambda, here 1 minus lambda, 1 minus lambda. So if you cross multiply, it is 1 minus lambda square. So their characteristic equation is same, okay, but these two matrix is not similar. That means we cannot find any non-singular matrix P for which it would be like B would be P inverse AP, but B is not equals to P inverse AP for some non-singular matrix P. Okay, so how we find this non-singular matrix P? Like if we arrange the eigenvectors in vertically, then we normally get the non-singular matrix. It's need to long calculation, that's why I avoid here, but if you want to do, you can do that, okay, and these two matrices would not be similar. So that's it for this video. Thanks for watching.